Hello. Good morning. How does that sound? Sorry I'm late and just had a few things to set up. I'm going to pick up from where I left off. Can you hear me just fine? I'm going to do a sound check. Hold on. Wow, that's really loud. Let's try that. Is that any better? Oh well. I'm not sure what's up. Things. Good morning. I just find there's so much noise. There's just so much noise it's capturing. And I don't know why. I'm sure it's something I can fix on my end. It's not that loud over here. Anyway, I'll play with that again later. Okay, so I hope everyone's doing well. Buen día a todos. I want to pick up where I left off in Unit 4, probability. So I asked you to just work through probability, reading the notes and trying the exercises. Let's see what I left for you to do. Let me go back. I did all of this, and I asked you to try these problems. And there's a video here that covers the answer, so you should have a look for that. And then here, okay, so we discussed this as well. And that brings us here. All right, any questions about these? Well, we'll see this again. I'll talk again about independence, so we'll see another example of that. But in the meantime, you can review with the videos I've already given and the notes. So we went through the 5 rules last week, and the last one we actually used this rule, rule number 6, which is the general addition rule for any 2 events. So I'm just, again, formalizing, going through the rules, but you know the rules, right? The only thing that might have been new to you is this concept of independence. Otherwise, the rest was intuitive, I would say. You can disagree, let me know if you disagree. But this one, we actually use this rule, right? We use this rule, if there are 2 events and we want to know about their union, we add their probabilities and we minus their intersecting or overlapping event probability, because we're double counting the overlapped portion. So we did see this. Okay, so I'm going to start here today. I'm going to make this a bit bigger. And what I do here is go through the different kinds of distributions you'll see, and in a way reassure you that there's a lot to be done in statistics. You could take a whole degree in statistics like I have. You can do a PhD in statistics. There's lots to learn, but this is the foundation course, and so I'm going to outline here the distributions and how the distributions that we're going to cover in this course and how we make estimates using them. Okay, well, we can compute estimates or make predictions of events or outcomes. Okay, so I begin with discrete distributions. Okay, so these are distributions where the outcomes are a finite list. Okay, so it's just, you can actually list it. You can actually write down all the possible outcomes of the sample space, and then and you know their probabilities. So this is just an example. Here's an example here. So what I've done is, first, under the heading General Discrete Distribution, these were determined over time. Okay, so this data was collected over time, and then this distribution was derived. And what it captures, the variable that it captures, is the month that our robot arm will break down. So the chance that a robot arm used in manufacturing will break down, or the specific one, the chance that it'll break down in the first month is 5%. And so this is determined by observing a robot arm for several months and coming up with some sort of average here. And within 2 months, the chance of it breaking down is 25%. Within 3 months, it'll break down with a chance of 50%. And by the fourth month, in the fourth month, it has a 20% chance of breaking down. Okay, so these, to be legitimate, I write this is the outcome here, and this is the probability that the variable x, that's the name, will equal the value x. So I go through each of these, and the chance of that is known, and they sum in total to 1. So that's a legitimate distribution. So we can also graph it. Here's the graph. And it looks like there's no curve, like the normal distribution that we used before. There's just a spike. So this represents 5%. So the height is the vertical axis is the probability. This represents 25, that's 50, and then this is 20%. And if you were to stack them each on top of each other, that would total 100%. Okay, so there's no possibility of breaking down. We don't have values for 2.5 or 2 3/4 months, nothing like that. All we have is that it will break down in the first or within the second, third, or fourth month. Okay. So that's a general discrete distribution. Then there are discrete distributions with a pattern, and I focus on this course on the binomial, and then mention a couple of other types of known distributions or derived or distributions that are useful in estimation. They have a particular pattern. They actually have a functional form. Anyway, we'll talk about that more in Unit 5. Okay, there's actually, you can use the pattern, derive a function, and here use the function to calculate the probability. So this is just an example of a binomial distribution. In fact, we've seen this before, right? The variable number of tails and 4 flips of a coin. And this is actually an example of a binomial distribution. We're going to talk about, in a moment, we're going to talk about the criteria for a phenomenon to be associated with a variable that's binomial. These are the values, we derived these before. I showed you how to get those. And we see this particular pattern that makes it symmetric, and we'll talk about if that's a general property as well. Here you can see the pattern looking symmetric, right? This is the center, and on this side you have the mirror of this side. Again, we write the x down on this horizontal axis, and the vertical axis has the probability. All right, so what are the properties for a variable to be binomial? Remembering about flipping a coin, what we're looking for was the number of, we defined as the number of tails and 4 flips of a coin, right? That's how we defined our variable. Let me just pull that up again. See, number of tails and 4 flips of a coin. So we're counting. This is a counting variable. We're counting the number of tails and 4 flips. So don't get confused by the two values. The number of successes, we're going to define it as the number of successes from exercise or problem to problem that we're going to repeat several times. We're going to repeatedly observe a phenomenon, and we're going to count the number of times we see what we're looking for out of the total times we look or observe. Okay, so that creates a general statement for the variable. So from different phenomena, as long as you identify what it is you're looking for and how many times you look, you're on the road to identifying a binomial random variable. So you need to confirm that each time you look to observe a success, there's either one of two possibilities, a success, and if it's not a success, it's a failure. Now these are harsh terms, but they're used in statistics to speak about the phenomenon of interest and anything else. Okay? So in our example of flipping a coin, each time we look for a tail. Tail would be a success, and a head would be a failure, because there's only two possibilities. So you got to be clear about there's only two possibilities. So those are the key things. Two possibilities for each observation. Second, the chance of observing your success is known. That's a key word. You need to know it, or you can't derive the probability distribution for it. And because it's so important, it's actually a parameter for the variable. Once we know it, we can use it and something else to derive the form, the functional form of the variable. So P is the name we give to the probability of seeing what we're looking for. We look several times, and we have to be more specific. For it to be a binomial random variable, we need to know the number of times we observe. Now that might not necessarily be the case. You might be interested in a variable where you keep on observing until you see what you want to see. So you observe once to look and see if someone is sick. Let's say you're looking for, you're testing people if they have a coronavirus, right? So you're using a test and you're repeatedly looking to see. And so the time, or the number of people you have to observe before you see the coronavirus, that's not the same sort of, it's a counting variable, the number of times I need to see before, I need to test people before I see someone with coronavirus. That's counting, but that's not binomial, okay? Because I need to know the number of times in order to derive the functional form of the binomial. The number of times are known as the n-independent trial. So each time we observe, the chance of seeing the the thing we're looking for is the same. Okay, that's what independent means. So that's another keyword. I'll double underline it. Independent, triple underline it. And n is finite. So this is the idea that I already know in advance how many times I'm going to look. So if a phenomenon has these three properties, or criteria, and it is discrete, it's a count of the number of successes in n independent trials, where the outcomes possible are 0 successes, 1 success, 2, all the way up to n successes. So there's n plus 1 possibilities. Don't forget the 0. So if this is the case, or these are the case, then what you have is a binomial random variable. So let's try to determine, in this case, this example here, whether this is a binomial variable. Can't see the whole thing. There. Find the probability of seeing more than 5 people holding an umbrella on a rainy day. If 100 different people are randomly selected and observed having an umbrella or not. And I give you this number. The probability of holding an umbrella on a rainy day is 10%. Now this might be useful if you're the manager of a mall or large shopping center, and you need to advise your staff to put out either carpet to catch the rain, or, because as people walk in, they walk in with an umbrella and they close it indoors, maybe outdoors. And there's a lot of water, right, on the entrance of the mall. It's ironic. I've had this example in my notes for years. It actually happened to me that I slipped and fell at the entrance of San Patricio. What is it? The Galeria de San Patricio. Anyway, I fell there. Humiliating. It's on video. I didn't see the video, but I can only imagine. And it was a rainy day, and I stepped in. So the question is, do people actually have an umbrella? Are they spreading rain or water everywhere at the front? And we'd like to know how many people have an umbrella, so we can either put out, we can observe every 10 minutes to make sure the path is clear and there's no rain or residual rain at the entrance, and also maybe have some umbrella bags at the front. So this might be a practical question, right? And observing over time, we might have this information that it looks like about 10% of people have an umbrella. Sorry, the chance of a person holding an umbrella on a rainy day is 10%. So we might have that information, and we want to estimate the chance of seeing more than 5 people having an umbrella. All right. So you can imagine there's lots of questions, but I've framed it this way, okay? And with this framing, is this a binomial? Well, we can define X as a number of people. So this is like my success that carry an umbrella. So this is the success out of 100. So this is my N. So each time I look, the chance of them having an umbrella is 10%. That's my P. Okay, now it doesn't necessarily have to be independent, but I've assumed that it is, all right? It doesn't have to necessarily be independent, because if people come in, if you're counting individual people and people come in groups, sometimes people share an umbrella, so that would change your results. And it wouldn't necessarily be independent if you were calculating the probability for each person. So anyway, there's ways that I can complicate this problem, but I've simplified it in this way. In this case, the way it's been defined, this is a binomial variable. Okay, so you can read about that. And what I do with that information, then I can write this as x is distributed, remember that tilde symbol, as binomial, and I put the n first and the p second. Let me put it as a decimal. So this should remind you, when we did normal, I would write xn mu sigma, right? So the idea there is, if I know mu and sigma, I know the pattern of the distribution, and I can compute estimates of certain outcomes occurring. So here, if I know p and n, similarly, I'm going to show you in Unit 5 how we calculate probabilities of certain things occurring. Okay, so you guys can review that. So once you have the information, you see, for example, probability of more than 5 people out of 100 having umbrellas on a rainy day. I want to calculate this. Okay, so this also looks similar, but remember, this is for a new type of probability. And now, different from flipping a coin 4 times, remember when we flipped a coin 4 times, we made, we did our own list of possible outcomes. Remember that? So head, 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 and then one tail would be like, and you have to list all the ways of seeing one tail in 4 flips. So this would be 0 tails, 1 tail. So if you look back, you'll remember we talked about that, etc. Imagine if you had to write all the possible outcomes with 100. That's going to be huge, right? So we don't like to have to write that. However practical this type of a problem is, this is just like observing events. You know, it's like sampling, right? This is the equivalent of sampling. I'm trying to observe repeatedly whether, for instance, someone approves of government policy or not, or so it's like a poll. I could use this information. I can use this theory to make estimates of concerning poll outcomes. The issue is that this was for 4, where n was equal to 4. What if n was equal to 100? You would have to do you have to figure out all the possible combinations of 100 outcomes. So that gets messy. We don't do that. We actually appeal to mathematics, and statistics identifies a pattern, okay? And I'm going to teach you how to exploit that pattern, the formula representing that pattern. And to do that, you need the n and p. All right, so that's what we're going to do in Unit 5. So this is 2. We'll see that later. Unit 5 is divided into 2 parts, and the first one is bin for binomial. All right. So there are other distributions with a form where there's parameters with those parameters and meeting certain criteria, you can derive probabilities. One example is the Poisson distribution, and the other is hypergeometric. And I'm not going to teach you, I'm not going to test you on these distributions, but I have exercises in Moodle where you get to practice. So this just lets you see that there are all kinds of distributions with which we can make, we can derive probability distributions given their parameters. Similar to the binomial, binomial needs a p and a finite n. It needs to know, you need to know p, the probability of a success on each trial, and you need to know n, the number of independent trials. For the Poisson, you don't need to know n. It's actually that scenario of where you look at a phenomenon until you observe what you're looking for. So n is absent. And hypergeometric, it removes the idea of independence. Okay, so that's where you're observing events, but it changes from observation to observation. They're not independent trials, so they're sort of related. Anyway, you can practice those in Moodle, and they'll show up in Unit 5. All right, so here's an example. I would like you to take a moment and read this exercise and see if you can tell me if this is a binomial phenomena, if the random variable that comes from it is binomial, and if so, then you have to identify n and p. Okay, so I'll give you a few minutes for that. Okay, how did you do? So this is an exercise. You need to read and identify this problem. This is a very practical problem. We'll give you some other exercises like this when we get to Unit 5. You need to identify whether this is a binomial setting. So we're going to test if someone has ESP. The experimental will look at cards that are hidden from the subject. Each card contains either a star, a circle, a wavy line, or a square. The experimental will look at each of the 100 cards in turn, and the subject will try to read the experimenter's mind and name the shape on each card. If a subject gets at least 50 correct, they will have demonstrated that they have ESP, extrasensory perception. So X is the number of correct guesses. Then X is binomially distributed with parameters N and P. So if this is the case, then what is N and what is P? Let's go through the criteria in turn. What is a success in this example? How will you define success? Yes, Gerardo, you're right. So success would be correctly identify the shape on the card. So each time, I'll say on a card. So each time we record if the person, the subject, is correctly guessing the shape on the card. And what is a failure? Just be incorrectly the shape on a card. Okay, so each time we record if the person correctly guessed. Say you take the test and guess all the way through. What is the probability that you will correctly guess one card? So what should P be? In other words, Gerardo said 50%. What do you think of that? Any comments? Omar is saying 0.01. That's not right. Well, think about it in terms of possible outcomes. And that will help you. either a star, a circle, a wavy line, or a square. So there's 4 possibilities. The chance of getting it correct, if there's 4 possibilities and they're equally likely, what's the chance of getting it correct? So we have to assume that, right? We'll have to assume each time a card is drawn, it's returned to the deck, or reshuffle the deck and it's returned. So maybe you didn't realize that. So what should be the chance? We did talk about this kind of an example last class. 4 possibilities, each is equally likely. Look back at the notes. There you go. Gerardo's got it. So it should be 1 out of 4, or 25%. All right, so that's how you have to think of that one. And how many independent trials are there? In other words, how many times is the person going to be guessing, repeating the same exercise? 100 times. And each time, the chance of him getting it right is the same, 25%. Okay, so this is a binomial. Those are the parameters, and we would write x is binomial with n of 100 and p of 0.25. Good. Good. Thank you for attempting that. Okay, so that's done. So what I've said is, for discrete distributions, in this class, we're going to talk about general discrete distributions, where I just give it to you and you have to work with it. Or you're going to have the binomial distribution to deal with, and I'm going to teach you how to answer questions using it. So there's 100 possibilities here, and let me just outline what more needs to be done about the binomial, because it doesn't end here. I want to talk about, in Unit 5, what's the probability that someone is found to have ESP? So the definition of having ESP is that the person has correctly guessed 50 or more cards. So that's what we want to find out. So that's to be continued in Unit 4, right? 5. But for now, I just wanted to introduce the concept of the binomial distribution. And you can see this is a very important distribution. It's used in sampling and estimation. All right, so then the second set of distributions, we start with the discrete, are the continuous distributions. So I just wrote some examples here that I'm going to talk about. The one that I used a lot in Unit 2 was, it would have been, Unit 2 normal distribution was the height of women, right? Height of women 18 and over and in feet. The sample space is made up of all possibilities in the range of 3 to 8, but all of them, all fractions are included. So the probability distribution is best represented by the normal density curve. So the normal density curve is not a spike density curve. It looks like this. It's smooth, right? And that's how we talked about it. So we already know one continuous distribution. We know about it. And we derive probabilities as areas to the left, and we have information on those probabilities in the Z table, and I taught you how to get those out of Excel, etc. So this is different, right? This is a different approach to working with the with making estimations. Another kind of distribution that's also continuous that I want you to know about is known as the uniform distribution, and I'm going to talk about that. So for example, define X as the number of hours students studied on a certain day. So this is a day before a test. And permitting fractions of an hour, a student could study between 0 and 16 hours if you include 8 hours for eating and sleeping. Sometimes you skip that when you're really cramming for a test, right? But let's just say that's... So we're going to assume, or let's say we have some information to suggest that behavior follows a uniform distribution. A uniform distribution looks like this. So it is continuous. It's set up between a lower and an upper bound. So this shows 0 to 16 hours of studying. And we assume uniformity. It means that any equal block of study hours, no matter if they're a low number of hours or a high number of hours, is equally likely. You see, that's what the box gives you. So it's sometimes interpreted as every outcome is equally likely, like, although, this is continuous, right? So we don't calculate density at a certain value. So because of its continuous nature, we always talk about the range of values instead. But in fact, at every single value, they all have the same height. All right? So, like this is 4 hours of time. It's equally likely for a person to study 4 hours or 12 to 16 hours. So this chance is the same as this chance. So these are, these define the box, the rectangle. Now, because all I need to know to derive areas under this curve, even though it's not a curve, it's a box, but we'll talk about the curve, even though, the rectangle is all I need to know, right? I need to know the dimensions of the rectangle to be able to interpret or compute areas. So really the parameters for this problem, for this type of distribution, are just the upper and the lower ends. As long as I know those, I can estimate certain outcomes. So because of that, I define the uniform distribution with a U, and I include the lower and the upper bound. So let's see how we can use this distribution to do what I'm saying. I'm going to erase this. And let's say I wanted to know what's the chance. Notice how I use similar looking expression, but it refers to this distribution that's different than normal, right? This is the uniform. So I draw this picture with 0 here and 16 here, and I want to know the area of this rectangle. That's the chance that someone studies between 0 and 4 hours. Well, to calculate the area of a rectangle, that's height times width. Well, I have the width. The width is always computed as the upper minus the lower end. So maybe not the full upper, but of this rectangle itself, it would be 4 minus 0, so that's 4. So that's the width. The height, I'm told here it's 1/16. How did they get that? How did they get the height of 1/16? Does anybody know? Can anybody tell me? No. All right, so we know the area under a curve or density curve has to be 100%, right? So let's look at the total. To figure out the height, we know that about the whole thing. I don't necessarily know at this moment how much this is, but I know the whole thing must be 1. And how would I get that? Area is equal to height times width. The height is what I want. The width is, well, I'll use the rule again, upper minus lower. Upper minus lower of the whole thing is 16 minus 0, or 16, right? I'll put 16 minus 0. So it's really height times 16, and this has to be 1. So does everybody see how I know that height must be 1 divided by 16? It's algebra. This means therefore. I have to move this over. So it's the picture, the drawing is deceiving. The drawing is deceiving because it looks higher than 1/16, right? Oh, I gotta fit this on. There you go. So what does that give me? So I know from that, so that should be immediate. That's how I got this. And so all I have to do is multiply 1/16 times 4 for this width, and so this is 4/16 or 1/4. All right, so that's how we work with uniform, and I'll give you an example in a moment. We'll work with that as well. Okay, so keep in mind what we know about continuous distributions. In continuous distributions, the probability that of an event exactly occurring, x equals x, we say is 0, right? It's for a continuous distribution. We only calculate the range, the probability for the range of outcomes, not for a particular outcome. You can think of that as there's infinitely many possibilities. The chance that it's just precisely one of them is not how we use this graph. We don't use charts for that. Anyway, it's a limitation of continuous distributions in a way, but I only can calculate for the range of values. So when I write this, it's around 4. All right, so what else in terms of continuous distributions are there for this class? There are the normal distributions, which we've already discussed, including the standard normal. And later in Unit 6, we'll talk about the t-distribution. I think I might talk about, well, it depends if we get there, the chi-square, but I think it's just the t that I require for tests. Okay, so let's try this exercise down here. I just put a summary of what I said in this box here. Why don't you try this one? I'll give you 5 minutes to try this. Okay, and I'll be right back. All right, how's it going? So what you should have done is taken a moment and drawn the box. All right, how's it going? Oh, you're gonna have repeat. So what you should have done. Sorry. Maybe I should use this shape here. Let's see. No, that didn't work. Oh, it makes a straight line. Okay. That's good. Oh, I have to hit it each time. Cool. Okay. All right, so there's my box. And it's going to run between, so this is X is uniform between -3 and 10. And I'm being asked, what's the chance that X is greater than 5? So where would 5 be? So this would be, I will make this 0, and I'll put 5 here. Okay. All right, so then what's the probability X is greater than 3? So I mean 5. So I want to know this. And what is the probability that X is negative? So that would be this, right? So the questions probability X greater than 5, it looks like it's like a normal distribution and I standardize, but that's referring to this uniform distribution. So you need to go to the box method. So you're going to say 5, so this is height times width. I'm just going to use H and W. So the height, we need to get the height. We know the width. The width of this is the upper one minus the lower one, right? Continuous distribution. So this is going to be I'm doing the calculations because you'll see you need that to be clear. Okay, so then height we got to find. Height in general, area is equal to height times width. So I want the height, but I want the area of the whole thing times the width of the whole thing. So what's width for the whole thing? The whole box is upper minus lower, which is 10 minus 3, be careful, and that's 13. So this is 13. So that means the height for the whole thing is 1 over 13. So this is 1 over 13. Again, it's not to scale. That's okay. 113 is very small. It should be really flat like this, but It's fine, as long as I write the numbers on it, you should be able to follow along, because this is a better drawing than if it was just this little thin box. All right, so that means that I have height is 113 times width of 5, which makes the answer 513. So this is 513. So we're done. So the first one is done. How about the second one? X is negative. Probability X is negative, so less than 0. So that looks like this. Same approach. Height equals height times width equals height is 113 and the width is 3. Does everybody agree? So this is 3/13. So that's how you deal with the uniform. So this is just, it's not hard. I have other shapes for distributions, and you can work on the exercises for that. In the tests as well, you see distributions that are different shapes, triangles, polygons. You should be able to work with them, okay? The principle is that the area under the curve should be 100%, and then go from there. Any questions? So this is uniform distribution. There are other shapes that you will see. So that's basically it for, maybe I should add that to the list here. I'll add to the list of other continuous distributions. Okay. You should know the area of a triangle, and I'll give you those formula, so you'll have those to work with. Okay, so that's that. All right, so what I want to do next is work on this exercise. Now you have the answers for this, but really understanding what's going on is the most important thing, not just getting the answer, okay? So I'm going to spend maybe half an hour on this. And then the rest of the class will be base formula and rules of means and variances. So let's see if I can leave you for a few minutes to work on at least A and B. So try these. All right, how's it going? Did you get a start on it? Questions? Okay, so you have two boxes. These are the balls contained in the boxes. You select one ball from the first one and randomly select another from the second. So a problem like this, when you have two different things happening and you're considering the mutual events, right? What you should do is create a matrix. Remember, we saw this with gender and occupation. So let's set up a matrix of outcomes. I'll do that here. So we could have box one. I'll make it more. The outcomes are 1, 2, 3. I'll make it bigger. 1, 2, 3, 4, and 5. And box 2, 1, 2, 3, or 4. So here's your matrix. And the possible outcomes are 1 with 1, 1 with 2, 1 with 3, 1 with 4, 2 with 1, 2 with 2, 2 with 3. I'm putting the comma so you don't think it's a double digit number. 3 with 1, 3 with 2, 3 with 3, and 3 with 4. 4 with 1, 4 with 2, 4 with 3, and 4 with 4. 5 with 1, 5 with 2, 5 with 3, and 5 with 4. And there you go. Those are the possible outcomes. So you can just make this. You could say something like, this is S, the sample space. All right. And does that answer the first question? The outcome of interest is the set of numbers on the two balls that are chosen. What is the sample space? So that's fine. In the notes, it shows them with all listed in a row. But this is sufficient for me. Okay, the next question is, let X be the sum of numbers. Okay, so we have a different definition for a variable or outcome. So X is the sum of numbers on the two selected balls. Again, we'll have a matrix, but rather than putting 1, 1, 1, 2, I'm going to sum the values. So I can make another, I can make another box with the sum in it. So let's do that. I'll put that below. Just below here. So that's going to look like box 1, box 2, and we're going to put together 1, 2, 3, 4, 5 with 1, 2, 3, and 4 and sum. So this is 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8, 6, 7, 8, 9. Again, a matrix, but different elements. I lost my, let me go back there. Why would it do that? Let's put those together. Okay, so let's put those. I lost the 7. I don't know why this happened. There's got to be a simple explanation for why this happens. Okay. So that's the second as part B. Okay, so but the question is, find the probability distribution. So this is a little bit different because in this problem here, part A, each of these had one in 20 chance of occurring, correct? Because there's 5 times 4 or 20 possibilities and they're all equally likely. So it's 1 in 20 chance. Down here, down here, 2 can only occur in one way. It's a 1 and a 1. But 3 has 2 ways of occurring. It could be 2 from the first box and 1 from the second, or 1 from the first and 2 from the second. So this changes the possibility of seeing the different outcomes. So what do we do here? So what we have to do is identify how many of each type. So let's do that. So there's 2 3s, there's 4 4s, there's 5 5s, there's 4 6s, 3 7s, 2 8s, and 1 9, and 1. All right, so those are the possible outcomes: 2, 3, 4, 5, 6, 7, 8, and 9 with different probabilities. Remember, each single one is 1/20th from what we saw above, but the chance of seeing, although the chance of seeing a 2 as a sum is 1 out of 20, the chance of seeing 3 is 2 out of 20, and the chance of seeing 4 is 3 out of 20, and 5, 4 out of 20, etc. So we have to write that down. So now we have a chance to apply what we learned about making a probability distribution. I'll just put it right here. I'll make it a little bit bigger. So I'm going to say the probability x equals little x, and this is little x. The outcomes are 2, 3, 4, 5, 6, 7, 8, and 9. And 2 has a 1 in 20 chance, 3 has a 2 in 20 chance, 4 has a 3 in 20 chance, 5 has a 4 in 20 chance, and then, let me confirm that, let's go see. So 2 has a 1 in 22, 3, 4, and also 6 has a 4 in 20 chance, and then it goes down from there. And the total is 20 out of 20, or 1. So that is the probability distribution. Questions? So again, you might have done this already, but please pay attention because I want to emphasize what's important here. It's an excellent example for visualizing the concepts of relationships between events and their probabilities. All right, so we have this distribution. Now what? So define the events A, ball drawn from the first box has an even number, B, sum is odd, and C, sum is 9. So these two, B and C, refer to this probability distribution, so we're going to use that. And then we're going to find the probability of each of those events, and in the fourth part, we're going to talk about their relationship. Okay, so we have a little bit of everything here. All right, let's see. Ball drawn from the first box has an even number. So what I'm going to do is I'm going to appeal to this drawing here. I'm going to redraw it. Or maybe I shouldn't, because you need it, right? Maybe I will draw it again. I'll redraw it, and I'm going to look at it in a different light. So I'm going to make it bigger. I'm going to put it here. Okay, so I just redrawn it. Now we're going to use it to answer these questions here, or to identify these events. So the ball drawn from the first box is an even number. So that would be this row or this row. So visually, let's use red. So red is A. Okay. Let's use blue for B. And that's the sum is odd. The sum is odd would be 3 and 3, 5, 5, 5. Okay, those 7 and 9. So blue is B. And I will use green for C. And I'll just make a mark like that. So that is, well, it looks like I'm scratching it out, so let's not do that. Let's just make a double circle on it. All right, so the only place where the sum is 9 is here. All right, so now that we have it color-coded, it's easier to see their interrelationships. Find the probability of A. So this is not going to be so hard, right? Because we can see the events, and I see, oh, I shouldn't, let me erase that. Can I erase that? I don't want to touch that because it makes it look like there's more. I'm going to write 2. I have to make it finer. 2 and 4, and I want to finish that there. Okay. So what's the probability of A? Well, that's easy. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the probability of A is 8 over 20, right? Because there were 20 possibilities, but for A, only 8 of them out of the 20 comprise A. So the probability of A is 8 out of 20. The probability of B is, let's count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 20, or it's easy to simplify that into 50%. I'll leave it as 10 out of 20 though. Basically half, right? Leave it like that. And then C is only one possible way of seeing C, so that's 1 out of 20. All right. Any questions so far? All right, let's look at the interrelationship now. So now I want to know about the probability of A and B happening, B and C and B, sorry, A and C and B and C. And then I want to know about their, what would they be? Are they disjoint events, independent events, or neither of those, just overlapping events? Now we can see it very clearly here. Well, I don't know if it's clear, but with the colors. So A was red. Do A and B overlap? Red and blue, yes. They overlap here, here, and here, and here. So the chance of A and B both happening at the same time are 1, 2, 3, 4 out of 20. Alec is asking, are A and B asking for the same thing, but even and odd? No, because A is that the first number, the ball from the first box is an even number. It's not just picking up the even numbers. It's picking up all kinds of numbers, okay, odd and even. Okay, I hope that's better. All right, so then the question is, let's stop here. What is the relationship between A and B? Are A and B disjoint? Well, no, because there's an answer. They'd be disjoint if the intersection was 0. But it's not, right? It's the actual value. So they're overlapping. Are they independent? How do we figure that out? So remember last class, let's do this on the side here. A and B are independent if probability of A and B is exactly the same as probability of A times the probability of B. Let's check. So the left-hand side is probability of A and B. That's left-hand side. So we just calculated that, right? We observed, and this is 4 out of 20. So let's take the right-hand side now. Probability of A times probability of B. Well, probability of A was 4 out of 20, correct? And the probability of B was 10 out of 20. Is that right? Oh no, see, it was 8 out of 20. Let's fix that. And then 10 out of 20, okay. 8 out of 20. All right, so this was 8 out of 20. And that's 10 out of 20. And if you simplify that, you might do this different than me. I'm gonna do it this way for people who don't like fractions. Okay, let's say this would be 2 out of 5, and this is 1/2, right? So those just cancel. Did I do something wrong? Nope, that's right, because it turns out if I simplify this one here, this is 1 out of 5. If you want to use fractions, that's fine too. To see this result, so it turns out that the chance of A and B happening is the same as multiplying A's probability by B's probability. This implies that the events are independent. Now this might just look all mathematical, and how do I know, like, what is this? What is she doing? Okay, this is a technical proof. This is a proof. You can use this approach when you don't know where to start. But if we look at the drawing, we can see the same result very easily. So let me conclude this statement here. Let's conclude this with this statement. Therefore, no, so since the left-hand side equals the right-hand side, A and B are independent. Now, if you don't like this way, let's try the next way of doing this, or making this proof. Looking at the drawing, look, remembering B happens half of the time, right? So B was the blue. It's half of all the possible outcomes are blue. Now let's look at A for an instant. A is the red. Within the red, how often does B occur? Right? That's looking at it this way. What's the probability of B given A? So within A, what's the chance of seeing B? Within A, it's half of the time It's here and here, and here and here. So within the domain of A, you see B half of the time. It turns out that this is the same as the probability of B. What was the probability of B again? It's 10 out of 20. Well, what's 10 out of 20? 1/2. So what's happening? It shows that whether I'm looking at all of the possible outcomes, B is half of them. Even if I'm in A, B is half of them. So it doesn't matter that A happened, the chance of seeing B remains 50%. That is an excellent example of independence. B's probability isn't affected by A happening. So there's this way of showing it. It's so nicely done here. And then there's this other way of showing it. If you don't have any rhyme or reason to where the numbers come from, but just a distribution, you can do it this way, down here. But if you have a drawing to go by, a depiction of the relationship of the events and their outcomes, you can just do it this way. Any questions? So you can rewatch this video to understand that better. But I need to move on because we still have a couple problems to do. So what's the chance of A and C? So remember, A is the red and C is the green. Do A and C ever overlap? Does A overlap with C? No, the blue and the red, the green and the red never overlap. So A and C has a probability of 0. And they are disjoint. They never overlap. Comments? What about B and C? B and C, so the blue and the green, they overlap. They overlap just here on 9. The probability then is one out of 20. And they are not disjoint because they actually overlap. They are not independent because the probability of C is 1 out of 20. But the probability of seeing C given B is not 1 out of 20. B being the blue, C is it's not going to be 1 out of 20. It's going to change, right? Because it's going to be out of this set, which is not 1 out of 20. It's going to be 1 out of 10. So it changed. In fact, maybe I should write a little bit more about that. We can check. Let's do that. I'm going to make the point here, and then I'm going to do it, the little check that I taught you before for practice. The answer is actually neither. So let's try that. I'm going to follow along with what I did before. We're going to check, the probability of B and C equals probability of B times C. So left-hand side is equal to B and C, which we found out was 1 out of 20, right? And what about the right-hand side? Is equal to probability of B times probability of C. Well, B's probability was 10 out of 20, and C's probability was 1 out of 20, which if you put those together, just making sure I did this right, it's 1 out of 40. Is that true? Did I do something wrong? Let me go back here. That doesn't make sense. So C was 1 out of 20, B was 10 out of 20. On the right-hand side, B times C, this times this, left-hand side, B and C. Yeah. Okay. So yeah, it's just not the same. The point is it's just not the same. So B times C would give and you'd say since left-hand side is not equal to right-hand side, B and C are not independent. Again, you can do it this way, or you can just look and see that C goes from 1/20 chance to 1 out of, it changes anyway. It goes to 1 out of 10, because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it's 1 out of the 10 within the blue set. So it changed. And it's not calculated this way. All right, so that's it. That's what I wanted to show you there. It's 11 o'clock almost. And what I want to do is to look at Bayes' rule. So we'll finish all of these yourself. You see the shapes I mentioned. You can try semicircle. This is for getting the probability distribution, or using this as the density to solve problems. It's try those. Here are all the answers and quizzes, and this brings us to this Bayes' rule. So you get to encounter Bayes' rule in the practice questions, the quizzes in Moodle. You get to practice with this, and it's a really important concept to know. However, I will not test it on the final exam. I will test it on the midterm test. So you need to practice this for next week's test. And here's a very useful example. The main challenge in solving problems using Bayes is interpretation of the problem, okay? That's usually the problem with most issues that students have, is just interpreting the problem. So here's the example. 2% of the population has a particular disease. So it's a very low prevalence. However, 3.2% of the population tests positive for the disease. So does anybody see a problem with that? What's the problem with this situation? 2% have a particular disease, but 3.2% of the population tests positive. What does that tell you? It tells you that the diagnostic test is inaccurate. The diagnostic test for the disease is inaccurate. In other words, a test for the disease is not perfectly accurate. Okay, so from a population-based study, this is a broad database with everybody in a particular population recorded there and their health outcomes. So it's a population-based study on people with the disease. It was found that 75% of them tested positive. So what are you getting here? You're actually getting a conditional probability. This is a group of people with the disease. Okay, so this is a defined population. So given that people have the disease, the chance of getting a positive result is 75%. It should be 100, right? But it's not. So this is an example of false negatives. So people are getting a negative test result when they actually have the disease. So for obvious reasons, patients who suspect they have the disease need to know what is the chance that they have the disease if they have tested positive. So, so far, all I've talked about are these different probabilities. Let's name them, okay? So let's see. 2% of the population has a disease. So this is the probability of disease. That's how I write disease, D+. However, 3.2% of the population tests positive for the disease. So what would we call that? Let's put a name on that. I don't know, my view looks a little blurry. I'm going to make this bigger. Let's see. That helps. You should have the notes in front of you. So the question is, what is 3.2? 3.2% test positive. So that is the probability of a positive test. And then we know that even looking at a group of people with the disease, the chance of a positive test is 0.75 to 75%. So there's going to be people getting a result that's negative, false negative, because they actually have the disease. So what I really want to know when I go and test for a disease is, what's the chance that I actually have the disease if I have a positive test? So this is what I really want to know. Do you have the dilemma? You got the idea? Getting a test result from a diagnostic test isn't perfectly accurate. There are possibility of errors in most tests. Okay? You could have a false negative, like in this state, where a person's saying they don't have the disease, but they actually do. Or you could have, and that could be dangerous, right? Because people will think they don't have it. If it's a contagious disease, they might spread it. The other thing is, it could be a false positive. You could be told you have a disease when you actually don't, and that can cause a lot of distress. So you really want, when you develop diagnostic tests, you really want to make sure to control against those two. So in the absence of a perfect world, we need to know these numbers. We need to know about the rates of false negatives, false positives, and really, ultimately, this is what you want to know after having a test result. What's the chance that I actually have the disease given I got a positive test result? So how will we figure that out? And what the heck does, can probability help us? Okay, so this is a conditional probability here. And I know that the probability of a positive test of having a disease given a positive test is actually equal to the probability of having both a positive test result and having the disease over the probability of testing positive. So this is from our understanding of conditional probabilities. Now we learned about calculating this result with multiplication if we know that the events are independent. If we don't have independence, what do we do? If we don't know that events are independent, what do we do? So I just take a moment to realize that the difference in this interpretation, this is not given to us, the probability of having the disease and testing positive. Okay, I interpreted this one as knowing somebody has a disease, the chance that they test positive. Or within a disease group, the chance of testing positive is this. That's different from this one. However, there is a relationship between them. What's the relationship between this and this given amount? Can anybody tell me? So take a moment to think this through. And I want to know if we know what this is in terms of the given information. And this is not multiplication, because I never said anything about independence. Well, isn't it true that if I don't know that they're independent, then I know that the chance of having the disease and testing positive must be equal to a conditional probability times the probability of whichever one I'm conditioning on. So in this case, I know the chance of testing positive for a disease group. So the chance of a disease group times the probability of testing positive for a disease group is the same as testing positive and having the disease. So I can exploit my understanding of calculating the intersection of events using the conditional probability for the one that I have information on. So essentially, I'm using the reverse condition to solve this one, which is really useful, really handy, and this is the interpretation used for a diagnostic test. So whenever you have a diagnostic test and you have a result, always ask your healthcare professional, what is the chance that you actually have the condition given the positive test? I don't think many patients know that. Okay. Now in this scenario, this was a very low prevalence of the disease. And with a low prevalence in the population, it turns out that actually having the disease given a positive test is also going to be very low. All right. So I'm going to calculate it now. Let's put this all together and see what we get. We know this value. We know this value. And we know this value. So we can calculate it. So let me give you a moment to put that together and then I'll do it, okay? Nobody? Not yet? Are you guys there? I got 10 people watching. I'm one of those, so it's only 9. All right, let's see. Are you thinking this through? You know what I'm talking about? So I need to calculate probability. I'm just rewriting what I have up there. Of the disease if you have a positive test. And this will be equal to the probability of disease. That's not right. Times the probability of testing positive if you have the disease. So that's the numerator. Divided by the probability of a positive test. And I put those numbers in that I have. The disease was, right, 2%. The positive test from a disease is 0.75, and this is crooked. Drives me crazy when it's crooked. And the denominator is that positive test result is 0.032. When you put it all together, what do you get? Is equal 0.46875. It's about 50%. All right, so to recap, using the rule for conditional probabilities, conditional probability is equal to this. However, this can be derived and is interpreted or defined as the probability of one event times the probability of the other event given that first event. I could have written it alternate ways, but I chose to write it like this. I could have also written it, but it didn't serve my purposes. I could have also written it as backwards, right? But that didn't serve my purpose because this was the one I was given. And what I found out is in a low prevalence population, the inaccuracy of the test implies that a positive test only means you have the disease 50% of the time. Not so accurate. Did you know that this is the same thing for the PCR test for coronavirus, for SARS-CoV-2 that everyone's concerned about? This is the same thing. It's a coincidence, or maybe not, that this is in my notes, but this is the case. And I'm going to put a clip with Dr. Birx from the U.S. Task Force on Coronavirus making this precise statement. So many conclusions come from here, but one is that's really important. but in terms of coronavirus, is that people from a low prevalence population shouldn't interpret the tests as accurate. I mean, the result of a positive test is only accurate 50% of the time. All right. So I put the clip in it's a very short clip. I put it in the chat. And I mean, I guess I could show it. It's a minute. Let's see if I can set it up fast enough. Okay. Can you see this? All right, I'm going to play this.
30 seconds on testing. These tests are not 100% sensitive or specific. And I'm going to go over this over and over again. So if you have 1% of your population infected, and you have a test that's only 99% specific, that means that when you find a positive, 50% of the time it will be a real positive, and 50% of the time it won't be. And that's why we're really asking people to start testing in among the first responders and the healthcare workers that may have had the greatest exposure, because that's where the test will be most reliable. And then when we have the luxury, we can go out to broader and broader communities. But this has been the fundamental question to begin with, and has been persistent. And we will emphasize to the American people again, this is a highly contagious virus. And we don't know by looking at someone whether they have pre-existing conditions or not. And so all of us, as far as protecting others, must continue to do all of the recommendations to ensure that when we are in an asymptomatic state, we're not passing the virus to others.
All right. I hope you heard that. Anyway, you can rewatch it if you need to. I put the clip in there. Okay. So this was this leads us to Bayes' rule, okay? What Bayes' rule is, what it does is it allows us to fully expand this expression. So the numerator I've rewritten as this, the definition of intersecting events, or the relationship between conditional probabilities. So anyway, so this, if the events are not independent, then you would calculate the intersection of probabilities this way. And it also expands the bottom if I didn't have information on the probability of the conditioned event here. So to find out the probability of event B given A, I can use information that I had about B. And that information, you see, given B, as long as I know its probability and the event A occurring in the subset of B, or when B occurs, if I have those two probabilities, I could actually find out the reverse in the event that A happens. And you see here I've expanded the bottom. This should just be, this is actually equivalent to that long string is equal to probability of A, because it says, this says the first expression is simply the probability of the probability of A and B, and this is the probability of A and not B. And together, if I add those together, what I have is the probability of A. A is made up of A and B happening, or A and not B happening. That's all the ways we can see A, if those are the only two events that involve A. All right, so Bayes' rule helps us find the conditional probability of being given A, knowing the reverse, A given B. So I have many examples for that, and you guys can practice. Like I said, it's not going to be on the final exam. It's just for practice in the quiz, online quizzes, and also for the midterm. You have to solve some not too complex problems, but like this can look really complex, but if you just pull back and remember what you're doing, like I just did here, it makes more sense. Oh, I'm too zoomed there. All right. So you guys can practice that. It's 11:30. Okay, so next. Oh dear, look at all this, right? So this is actually not as bad as it looks. I don't know if I can finish this in half an hour though. All right, so rules of means and variances, all of this stuff brings us here. What I really want to be able to do with this, in the end, it looks very technical, but it has very practical applications. So all I need you to remember are the main results, okay? So I have a lot of derivation in the notes. That's for me. Like I want to take you, I'm building bridges, right? I told you. So I'm trying to take you over the bridge. I'm trying to show you how we get from one to the other, not just showing you results. But in the end, we just use the results. So let's just apply the rules to this exercise, which I didn't give you an answer for, so I want to do it now. And then tell you that what I want you to be able to do for the test are problems like these. And I give you the answers for each of them so you can practice. So I want you to spend this week practicing solving these problems. I have all the answers given to you here so you can practice. So let's review, using this exercise, the rules, or some of the rules. So I'm going to unzoom this so you can see this better. Okay, so each year, employees for a large company receive a Christmas bonus of $500, plus $100 for each year they have worked for the company. I don't know, this looks blurry to me. Hold on a second. See if I can fix this. I don't know why the feed looks so blurry. I'm not giving up on this. Let's see. Anyway. All right, so each year employees for a large company receive a Christmas bonus of $500 plus $100 for each year they work for the company. Therefore, if X is the number of years an employee has worked for the company and Y is their Christmas bonus, we can get one from the other. Okay, so this is the relationship. It's the relationship between X, the number of years, and Y, the Christmas bonus. All right, so there's a relationship that I multiply a number and then add another number. When you do that, when you multiply numbers and you add constants, this is known as a, I don't want to be too fancy about it, but it's known as a linear transformation, right? It looks like a line. Okay, but what's happening? So I have all this information in this company about the number of years an employee works. And from the information I have, I'm able to calculate the duration of employment on average and with a standard deviation. So I have this really great information that they work on average 6.7 years with a standard deviation of 2.4 years. So this is like, since it's a large company, I can say mu, and this is sigma, right? So it represents the population parameters for. Now I want to use that information that I've gathered over several years. I want to relate it to another variable without studying that variable, because this is the first time we're going to give this Christmas bonus, or this is a, I don't have much information on this Christmas bonus. All I know is that I want to just take the number of years people work and times it by 100 and add $500 bonus, right? So they get a little bit more for the years they worked. Now, I could go ahead and study this for a while and get its mean and standard deviation, but why? Like, I already have the information on X and it's related by a linear transformation. Isn't there something I can derive from this? Like, are there properties of y that I already know because I know x? Well, in fact, there are. Notice I didn't tell you what kind of distribution x is. I just told you its mean and standard deviation. Okay, without knowing the distribution, I can I can deduce from x properties of y, in particular y's mean and standard deviation. So think about it for a minute. Even though I don't know the distribution, let's just use a kind of a shape. Let's say, let's just say x was shaped like this. Okay. So x is shaped like that, and they're telling us that x is 6.7 in the middle. So 6.7 years, and standard deviation 2.4. So it's not necessarily normal. I just drawn it like this because you can think there's a shape, right? So let's say if I multiply each value of x by 100, so I could create a new distribution. What would it look like? I guess that's the question. What would it look like if I did that? Now, you've seen this before. We did talk about this we talked about normal distribution, so I'm just going to use those results. So what would this shape look like, 100x? What would be the mean of 100x, a new variable? Well, if I took every value and multiplied it by x, I have to do the same thing to the mean value, right? And it really wouldn't look like this. Wouldn't it look, what would it look like? Can anybody tell me the shape? Or just give me an idea of the shape. What's the center? So whatever I do to x, I do to all its values, and I also do it to the mean. So this is actually going to be this is a new mean. So if this is mu of x, the mu of 100x is going to be 670. It's just times by 100. And all the values are going to be times by 100. So this is really going to be a way more spread out distribution. It's going to be a flatter distribution. Okay? So it's going to spread it all out. What if I add 500, to every value now? So I've done this, but now I'm going to add 500 to every value. So what does 500 plus 100x look like? What would be the mean? It would be whatever I do to every value, I also do to the mean. So I have to add 500 to it. So it's going to be 1170. So whatever I do to every value, I also do to the mean. So that's the new mean. Okay, all I've done is common sense here. But in general, the linear transformation, the effect of it, so this is called the mean operator. This is the operator for average or expected value. So if I put the operator on 500 plus 100x, the operator lets everything that happens to the values also happen to the mean. So in general, that's what I write for this problem, but in general, we say for this operator where I multiply every value of x by b and I shift by a, this will just be the same for the mean. So whatever I do to every value of x, I also do to the mean. All right, so how does this affect the standard deviation? Notice what happened here is it got flatter. So the standard deviation is going to grow, but by how much? What actually affects the standard deviation? Well, adding 500 didn't affect the standard deviation, right? Adding 500 only affected this value here, but really how spread out everything is, it stays the same. So it was only the value in front that affected the standard deviation. So we usually say, in general, that's my niece. 1 minute. I have to turn down the sound. I can't seem to turn down the sound. There. Okay. I'm going to write this in terms of the variance. The variance of a linear transformation it reduces to just remembering how we calculate variance, right? We square all of the deviations from the mean. The standard deviation is the square root of that. So the variance of y is just, it turns out the shift factor doesn't do anything to the variance. It's the factor of b. And just like every other value, the shift factor, the scalar, the multiple in front, also gets squared. So it turns out that the variance of y will be b squared times the variance of x. And now if I was to write that in standard deviations, where I can write the variance like this, right? And b squared variance of x like this, it turns out very simple that the standard deviation of y is just b times the standard deviation of x. So I'm going to just highlight that so you remember that. I'll move this down. Okay, where I can write this, I'm going to write this also as sigma y. Sorry, I did that wrong. It's not sigma y, that's mu y. All right, so the variance, this is the variance operator, the a drops out. The expected value operator, whatever you do to the values, you also do to the mean. So those are the two main results that you get to use to solve problems. So knowing this, for this exercise, what would be the standard deviation? The standard deviation you're told is 2.4. So here, the new standard deviation that I write as 500 plus 100x is going to be just 100 times the original one, 2.4. I'll write it down. All right, so that's the answer here. And that's the answer here. So your answers are mean, the new mean, (170) and standard deviation 240. So those are the new, those are going to be the bonuses, the mean and standard deviation of the bonuses. Okay, so what I've presented here in the boxes are the formulas that you need. Okay. So let's see if I've covered most things. There's more here, and I do have this presented in my videos. It's not as, it kind of goes on and on, I have to admit. But those are the main points. That's what you can read this easier now. Like I've used these examples that I provide And the formulas that I derive are only for discrete distributions, where I give you the possible outcomes and their probability, and I show you how to calculate them. Okay, my results are analogous for continuous distributions. But we don't handle them here because I'm not going to include calculus, where you would have to use integration to calculate those. So I go through all this derivation and all the symbols. Basically, you can just read through that, okay? What's really, really important in the end is that you know the result. But you see, the mean is just the weighted average by formula. And what are the implications of that? Because it's the weighted average, I can take an expression like a plus bx, and I treat every single value of x the same, right? So whatever I do to x, I do to the mean is going to be the conclusion. So I put it into this formula and I move things around and I demonstrate that exactly that. I'm doing this to, this is the treatment of x, and it should be the treatment of the means. So I derive them here, but all you really need are the results. As well, that's for means and standard deviations. And then I have something here about the sum and difference of means. That's really important. The rule for let's say you put two distributions together. So what this would be like in finance, where you have properties of one asset and properties of another asset combined in a portfolio. So you are going to be subject to the mean of the sum of those. Okay? And so whatever you do to the means, so how would I say this? So yeah, the sum, the mean of the sums, or the mean of the sum is the sum of the means. That's what I want to say here. So the mean of the sum, or the difference, let me do this, mean of the sum or difference of variables is the sum or difference of their means. All right? And I can derive this to prove this. And this is very important. Let's say, as I talked about the example here of putting two assets together in a portfolio and wanting to know what their new mean would be. How about if you have a portfolio already, call that X, and you take out one of the assets? How does that affect your average returns? That's also something you can calculate, okay? So that's important. Now what about the variance of the sum or the difference? That's all that remains, because I did all of this. The variance of the sum or the difference. The result that we just discussed was that the mean of the sum is equal to the sum of the means. Well, should it follow that the variance of a sum is the sum of the variances? This is only the case when your variables are independent or not correlated. Okay? In that case, the variance of the sum is the same as the sum of the variances. Also, the variance of their difference is the same as the sum of their variances. This happens. Why does this happen? Well, remember that a negative is like a -1 in front. And for variances, the scalar in front gets multiplied, right? It gets squared. So this -1 squared is just 1, and that becomes that. So the variability of a portfolio of assets is the sum of the variability of the two assets. And it's the same for the case that I explained. If you have a portfolio and you remove one of the assets, the volatility or variability is dependent on both. It's a sum of both. All right, so all I have here is the sum of and the difference of variances if they're independent. But what if they're not independent? What if they're interdependent? What do I do? I have these results. In general, the variance of a sum of variables is equal to what we had above, but an extra term, which accounts for their covariability. And similarly, when you subtract them, this is all the same, but this becomes a negative here, okay? So where does this come from? Actually, again, I have a video explaining this, but I think I have a little time. All of this will be on the test, Alec, all of this. If you have questions during the week, let me know. All right, so where did these come from? These look like very long formulas and very intimidating. And I reiterate them here because what I've done is I have substituted this for this term here. How did I do that? Well, remember what correlation is. So this is the symbol. So everything is in Greek letters here because I'm working with distributions, right? I'm working with the distribution of the population, in other words, of data. So I use Greek letters. And here it turns out, remembering what the correlation is, the correlation is the standardized covariance. So I could write it like that, or if I have the correlation, I could also write covariance as that. Okay, so depending on what you're given, if you're given covariance, you calculate like this. If you're given the correlation, you calculate like this. Now, where the heck is this formula coming from? And what in the world is this? I'm going to describe that in a moment. Notice all I've done here is x and y, but I could also have scalars in front. I could be multiplying x by something and y by something. So what I'm going to do is take a moment to show you the general case and the results that is here. And then what follows after I do this, you should be able to solve and understand all of these problems. So you can prepare for those during the week. Okay, so this is all going to be on the test. All of this is possible. All right. So where does this formula come from? What I'm going to do is consider variable ax and by So this is like a multiple of x or a multiple of y. And, oops, I'm going to use that thing again. Didn't work. Come on. Oh well. So much for that. All right. And then I'm going to think about, who's that? So yeah, I'm supposed to go for lunch, so somebody's calling me. Okay, so quickly, I actually have this video. You guys can have a look at it. I'm going to derive the formula. Oh goodness, I have to turn my volume down. Let's see. All right, so I want to consider the covariability of this variable with the other variable, okay, and itself. So I have to consider all degrees of correlation or covariance. So I want the covariance of AX and AX, covariance of AX with BY. I'm going to continue. If you have to go, go ahead. You guys can finish watching later. BY with AX and the covariance of BY with BY. So what in the world, what does this mean? This is the covariance of AX with AX. So what does that look like? So I'm going to appeal, even though I told you this is all for populations, I'm going to use the sample result because I think that one is much more, for historical data, rings a little more true, or it's a little easier to follow. So, especially better than the weighted distributions. Okay, so this is AX minus X bar squared. Oops, that's not right. So because whatever I do to the values, I do to the mean, it would be AX. And then I square that. So that is, sorry, no, that's variance, sorry. So I do that once, and then AX minus AX bar. So that's covariance. Oops, I'm leaving. So, okay, so this is covariance, and you have to look back at your formulas to remember that. So isn't it true that I can take that A out of there? And aren't these just the same thing? So really, doesn't this reduce to I can put it all the way here and call this isn't that true? Can't I just pull this out of here and pull this A out of here, and that makes A squared, and then that leaves two of these, and isn't that just variance of X? This and this before I take the square root for standard deviation. So really, I can write that, so this is going to be like, that means just kind of like, this is going to be like this in our symbols. That's variance, that's a squared. So this term, the first term, reduces to a squared sigma x squared. And this one down here reduces to b squared sigma y squared. And that just leaves these two terms. And with the same logic, you'll see that this reduces to covariance xy times the scalars, and so does this. And that is where the two covariances come from. So I've just shown you, and you can watch it slowly, or you can ask me this week to explain it again. I can make a video or meet you in office hours, online or in person, to explain to you this is where the formula comes from. A squared sigma x squared, b squared sigma y squared, plus 2ab, covariance. And that is not here because this didn't have an A and a B up here, but I could put it. So what I'm going to put down here, just so that you're not confused, hopefully, at this point. So this, what I found here is the variance of AX plus BY is equal to A squared sigma x squared plus b squared sigma y squared plus 2 AB covariance xy. And with that, I'm going to leave you to try the exercises where you have all the answers to work through them, and keep me posted if you have any questions. All right, there's some videos where I repeat these concepts. So have a great week, and next week, unless I hear from you, we're going to have the class and then the test. So I can answer some questions, and then I'll put up the test, and you'll have 3 hours for the test next week. Okay? Same amount of questions, but double the time. Any questions? I'm going to head out. Okay. I'll wait one more minute. Take care. Thanks for sticking around.